In today's topic in physics, we shall be looking at vibration in strings. Stringed musical instruments such as the guitar, violin or piano depend for their sound on the vibration of wire or string. Guitar, violin or piano are examples of stringed instruments. A stationary transverse wave is set up in the string whose fundamental frequency F0 of vibration is given by F0 is equal to 1 over 2L root T over M, where L is the length of the wire in meters, T is the tension in the wire in newtons, and M is mass per unit length of wire in kilograms per meter. The string can also be made to vibrate in such a way as to emit overtones, also called harmonics of frequencies. We have 2 F0s, we have 3 F0s, 4 F0s, and so on, which are referred to as first overtone, second overtone, third overtone, etc. respectively. If you look at the diagram here, the string is vibrating at its fundamental frequency F0. The end of the string here is the node, and the other end too is the node. Now between here, the space is the antinode. The length between this node and the other node there is the length of the string, and which is given as lambda over 2. The fundamental frequency F0 now will be expressed as V over lambda. But lambda initially is 2L. If you make lambda here the subject, you have 2L. Now substituting the value of lambda here, we have V over 2L. The string can be made to vibrate in many different ways, leading to overtones. In the diagram, we have 2 antinodes, A and A. And then we have 3 nodes in this diagram. We have this, this, and this. On the length of the string is lambda over 2, which is NN. And then we have another NN, which is lambda over 2. We are going to sum these two together to have a complete length. So we have lambda over 2 plus lambda over 2. Working it out, we are going to have lambda as our result. Therefore, length is equal to lambda. The first overtone or harmonic obtained here is given as V over lambda, which is also known as V over L, because we have L equals to lambda. So we can replace lambda here with L. This is a higher note than the fundamental frequency obtained before. But from the fundamental frequency, we have F0 given as V over 2L. Now if you make V the subject, you are going to have 2 F0L. Then substitute the value of V in this equation here. You are going to have 2 F0L over L. The L here and this L here will cancel each other. The result will be 2F. So F0, 2F0 now will be F1. F1 here is the first harmonic in the vibrating string. Second harmonic. This is the diagram for second harmonic. The distance from here to this point is the length, of the vibrating string. We have 4 nodes in this diagram. 1, 2, 3, 4. We have 3 antinodes here. 1, 2, 3. Take note, NN is lambda over 2. So the distance now will be NN, which is lambda over 2, NN, another lambda over 2, NN, another lambda over 2. And from here to here, don't forget, is the length of the wire. Now you sum this together. Lambda over 2 plus lambda over 2 plus lambda over 2. The result is going to be 3 lambda over 2. Making lambda here the subject, we are going to have lambda here as 2L over 3. Therefore, the second harmonic here can now be expressed as V over lambda 2. This lambda 2 is indicating the wavelength in the second harmonic. And this can also be expressed as 3V over 2L. If we replaced a lambda with 2L over 3, that will be the result. Now, from the fundamental frequency, we have V over 2L. We are going to make V the subject from the fundamental frequency. And there we have V, which is 2F0L. Now, substituting the value of V in this equation here, we are going to have 3 times 2F0L over 2L. 2 here, we cancel this, and this L will go with this. So we have 3F0. So the second harmonic will be 3F0. Example 1. The wavelength of the fundamental note of 1 meter long guitar string is A, 25 centimeters, B, 50 centimeters, C, 100 centimeters, D, 200 centimeters. Now we can solve that. Solution. Lambda, which is the wavelength we are asked to calculate, is given as 2R. But 1 meter is the same thing as 100 centimeter. Therefore, lambda now will be 2 times 100. The answer now will be 200 centimeters. We now go back to the option and look at the correct option. The correct option there is option D, which has 200 centimeters. Example 2. Which of the diagrams below represents the second harmonic of a vibrating string fixed at both ends? We have the diagrams here, A, B, C, and D. The correct option here is C. C has the second harmonic. D here has the third harmonic. So it's not the correct option. A is the fundamental frequency of a stretch string, and B is the first harmonic. So the correct option is option C, which has the second harmonic. Example 3. The diagram shows a stationary wave set up in a string which is fixed at both ends. If the distance AB is 2.0 meters and the frequency of the wave is 350 Hertz, The speed of the wave is A. 175 meters per second, B. 350 meters per second, C. 700 meters per second, D. 1400 meters per second. Solution. The formula here, F is equals to V over lambda. But we are calculating V, so we make V the subject. So V now will be F lambda. F is given in that question as 350 hertz. And lambda is given in that question as 2 meters from A to B. Therefore, AC will be 2 times 2, which is 4. Now, substituting this value into this equation here, we have 350 times 4. And 350 times 4 will give us 1,400 meters per second. Meters per second is the unit for velocity. So the correct option is option D, which is 1,400 meters per second.